Okay, well, welcome everybody to the Diffuse Gas and Cosmic Ecosystem Science Interest Group. If this is your first time here, welcome. If you're a regular, welcome. You know the drill. You probably know the website already. Looking forward, May 22nd, John Chisholm is on deck with a title TBD. And that segues really nicely into our current speaker, who also has a TBD in his title, Dr. Ben Oppenheimer, a pioneer of modeling the circumgalactic medium and all of the exciting physical processes that shape it. And so today, Ben is going to tell us about the CGM in 1D, 2D, and TBD. Take it away, Ben.
Okay, thank you, Jess, a longtime collaborator. Um, Thank you for this audience. I've gone through and I see familiar faces here, some who are relevant to this talk as well. And uh, so the list of speakers in this DGCE Science Interest Group has been great. So I'm honored to be among them. I hope I do a as good of a job as some of these other talks, which I have been, I think we've all enjoyed. So I am going to start out with this slide, which I made last week because I gave this talk, or a version of it, at the University of Hull, of all places, and they needed an introduction. And I didn't use the famous Jess Work, Molly Peebles, Jason Tumlinson artist rendition of the CGM. I have another one made by Glenn Kapsak and the Swinburne graphics design team. And I thought it was relevant because it shows what I'm going to simplify as kind of the three parts of this talk. Two of them are painted here. One is the extended accretion disk, or so we think, extending into the CGM beyond the stellar disk of the galaxy. This kind of AxiSymmetric component, or often modeled as. One is the gas carried out in superwind outflows in the redder colors here. And there's kind of an invisible component. Maybe this is not the best artist renditions. For the first part of the talk is a static hot gaseous halo, and hot is here 10 to the 6 Kelvin and above, or maybe 10 to the 5.5 Kelvin, which contrasted from the cool CGM, which is I'll talk about as well. Terms I will use are CGM. I had to introduce that term in this for this slide last week. I think we are all experts here. I'll go through things fast, and if I go through something too fast, just interrupt me because there's a wide range of interest here. I'll also talk about the intergroup medium and the intercluster medium. And the last two categories have been observed out to R500, indicating a gaseous halo, often described to be in hydrostatic equilibrium with the dark matter potential. Which brings me to my next slide, which shows this. This is an old slide from an ancient paper at this point, this Ben Moore paper, showing two halos separated by a factor of several hundred in halo mass. One's corresponding to the Milky Way, one the Virgo cluster, and I sometimes ask people which one is which. I forget which one is which in these dark matter only simulations. But the point is there's a high degree of self-similarity in dark matter halos. And there's some fundamental scalings that we expect here for energy and angular momentum, temperature, pressure as well, etc. So the question I ask, I've been asking for a while, is the CGM a scaled down version of the ICM? And the answer, of course, is no. But to get there, we have a wealth of observations. And those observations are, close to my heart, are UV absorption line surveys done by COS, Cosmic Origin Spectrograph, probing this phase space of redshift and halo mass in the evolved universe, and different ions and different halos that they correspond to, etc. And we're really looking at the Z below 0.6 redshift universe from a halo perspective here in this part of the talk. And the future, or the now and the future, is other gas techniques, probing especially the the static halo, or I shouldn't say static, the hot gaseous halo, and I shouldn't say only hot, but X-rays are definitely corresponding to the hot halo, which I'll term an atmosphere in this first part of the talk and refer to as 1D, a 1D component of the CGM, or the intercluster medium. But there's also other things like Sunayev-Zeldovich, thermal Sunayev-Zeldovich. I also see Cameron Pratt here, who has published some work on this. And I bet we're all excited about fast radio bursts, and I'll only touch on that. I don't have many results on that. And I also want to refer to last month's talk by Daisuke Nagai and the beautiful work of Isabel Medlock, who is looking at FRBs in camel simulations and other simulations as well. So now we have new windows into the CGM, and this is where I introduce the descriptive parametric model. This really came out of Halo 21, the KITP program, with Jess, with Mark Voigt, with Cameron Hummels, and they're all co-authors on this paper to be soon released. You can see it's pretty far along. It should have been released by now, but here's a preview. Cassius profiles for galaxies, groups, and clusters. So I will motivate this by those different, observation wave bands. I'll talk about 4 wave bands, and 5 observables, 2 in the ultraviolet. And the first one is the most obscure, but I think people here are more likely to understand it. Using cool UV absorbers detected in H1 low metal ions to fit cloudy models and derive physical properties like density, using a temperature in equilibrium around 10 to 4 Kelvin, corresponding to the cool CGM. These are cool clouds. I'll use the term clouds from now on to refer to these, but they can infer the pressure of the CGM, as has been done, in pioneering work by Jess and others here. So I'll touch upon that, but more massive halos have higher pressures in this Mark Voigt compilation. Oxygen 6, we love Oxygen 6. It's an inspiration for many models. And another thing with Jess, actually, CGM squared, and Chernyshov has a paper compiling those CGM squared and all the data sets taken with, especially with COS. Soft X-ray emission. I'll talk a lot more about soft X-ray emission here, but there is eROSITA results, 2-year results, ERAS-4, that is 4 surveys, 6-month surveys of the sky, stacking halos, because this all-sky survey is too shallow to detect individual halos around normal galaxies, but it can stack tens of thousands, hundreds of thousands of halos. Thermal Sunayev-Zeldovich, a shout out to Cameron Pratt and Joel Bregman, and others like Emmanuel Shan, and massive surveys stacking hundreds of thousands of halos at, usually of 0.3, 0.5. I won't talk about that as much today. And of course, we're all excited about fast radio bursts. And I can say that we don't really have constraints from fast radio bursts yet, but we want to get this model out, or these sets of models out, and this modeling formalism out for the FRBs and the detections of the electron, the ionized universe associated with the CGM. So the purpose of the DPM paper, I'm going to descriptive parametric model, I'm going to use that acronym throughout. And I just took this straight from the paper, from the introduction, is to introduce a new mathematical formalism. It's not that new, it's using existing profiles, profile formalism for the DPM, and I'll just describe that some more. I want to develop the tools necessary to derive mock observations. So that is software that's already been developed using other Python modules such as Trident, Cameron Hummels for UV absorption line, sightlines, and mock Voigt profile absorption, and PyXSim by John Suhone to mock X-ray observations, etc. And this is meant to be modular. So you can use DPM Halo, which I'll introduce in the next slide, to use as a set of gaseous halo profiles. So we also want to compile an initial version of a data library of observations for the four different wavebands that are available now. And that refers back to that phase space of the observations. And then what is kind of fun is to come up with some DPM models and fit them to, or see how they compare. We're not statistically fitting data here, but we want to see how they compare to existing observational surveys. I should say this is part of a Hubble grant, actually, cost, inspired Hubble grant from cycle 31, and it's pretty much done now. And I'm going to publish the results and give this tool to the community. So the descriptive parametric model is a set of physical profiles corresponding to three physical parameters: pressure, density, and metallicity. And from that, you can derive other things. The models are model profiles are a function of radius, mass, and redshift. So you have three physical parameters, as a function of three physical properties as a function of three parameters. So you have 9 variables. And then normalization. So Mark Voigt and I were envisioning this as like a 12 parameter model set. I quickly expanded it to, I think now 31, because I like trying to fit existing observational data sets quite precisely. So we use generalized NFW profiles with a lot of free parameters. And for this initial data, initial paper, we use clusters as a linchpin and introduce 3 types of models, or I call 3 models: model 1, model 2, and model 3. And for the next, 15, 20 minutes, I am going to talk about model 1, which is the self-similar model. If we saw that first plot of those dark matter halos, this is kind of the corresponding model where you have kind of self-similar models. The temperature goes as m to the 2/3, as you would expect from virial relations. But if you look at density, the density profiles would be lying on top of each other. This model is usually dotted lines when I show galaxy groups and clusters, so you can't see the galaxy and groups beneath that line. But they're grounded in observations of clusters from the X-ray. Really shout out to the XCOP group and Giordini, et cetera, using a kind of a mass selected sample of clusters. Now, how they scale down to the group and galaxy regime, the intergroup medium and the CGM regime, although I'll say that I think the CGM extends all the way up to the ICM and encompasses all these halos and all these gaseous profiles. But there's a couple ways to scale down. One is the cluster reduced, and those are often dashed lines in these sometimes confusing plots. So they have the same profile shapes for pressure and density, but they're scaled down more. So there are missing baryons in another phase, presumably. I'll talk more about that in a little bit. And then there's the slope changing model, which is, I think there's evidence out there for flatter profiles as you go down to lower mass, at least in the group regime. There's some direct evidence for that from the X-ray. So at that point, I will say again? Is there a question? Or maybe not. Okay. All right. Feel free to ask a question. Okay, I don't think so. But here we go. So here are the 3 physical properties as a function of different, or for different halo masses. And I plot a lot of things here as a function of fractional virial radius, or R200C. So going out to 2 times R200C. And you can kind of see that this is model 3, the slope changing model, and it's flatter pressure profiles, flatter electron density profiles. And I'm using the same metallicity profile for everything throughout. Now, the point is of this releasing this tool, which I'll call DPM Halo, and it's easy to install, is that you can change it. You can come up with your own model profiles if you so see fit. Or you can use one of the existing model profiles for some calculation of physical properties for some application that you might have. And people are often distracted by like kind of this kind of, point where everything overlaps. And that's just a coincidence of the parameter choice I show for model 3. But don't get too focused on that. But uh, from from these profiles, you can derive others I call secondary physical properties, such as temperature, entropy, baryon fraction, and cooling times. And of course, I flash a slide of all of those, which are in the paper. And I will go into gas fraction and entropy. I'm assuming thermal support, so the pressure is totally thermal. So in this case, and that's assumption you don't necessarily have to follow with this model. You could change that. But the temperatures here are on the bottom. I also look at cooling times. And I use different constraints for roughly for model 3, the slope changing model. So now what kind of is the fun part of this is to take these 3 models and throw them at different data sets, observational data sets across 4 wave bands. And I gave you a false choice here, and I actually feel bad because probably there's some people who want to hear more about Zeldovich and especially fast radio bursts. That's why the paper is going to be released soon. And every plot here you can actually, not every plot, a lot of these plots you can make right now. And I'll, if you so wish, I hope it's easy to do, and I think it is. But given this audience, I'm going to expose you to the X-ray language that I came up with, and it sticks, just figuratively, not literally, and touch on the 2 UV observables. Because I think given this audience, we want to think about the X-ray because it's an exciting time. Given eROSITA has released some of its data and observations observational results have been published from that. And Yi Zhang has published ERAS-4 stacks of X-ray emission around individual galaxies, but hundreds of thousands of them. And I show this plot on the left showing kind of a holistic measure of the X-ray luminosity, and in detail, it is the X-ray luminosity something between 0.15 and 1 R500 as a function of halo mass. And to motivate the different types of objects, there's a fit here from Aquino from individual objects of groups and clusters. They're actually weak lensing selected. And there's a fit to them. I don't show the individual data points. Look at other papers to see the individual data points. And then there's stacks from eROSITA. And already you can see that no model fits everything. And that's not the point of this of these models. But I will say that model 1 can probably be eliminated because that is the scaled down clusters, the self-similar clusters, scaled down to groups and L-star halos. And what you can see is the gas fraction, and there's that dashed line corresponding to the cosmic proportion of baryons, omega B over omega matter. And clusters are consistent with that, but groups already are not, as you can see from this Aquino line for gas fraction based on the observations on the left there. And that's why we have those 2 other models, the cluster reduced and the slope changing models. And there's a little more data, but you can see that model 1, the X-ray emission is too bright. And this is not a new discovery. This has been known for a quarter of a century now. ROSAT could not detect halos around individual L-star galaxies or passive galaxies. So there's already sort of like maybe a missing baryons problem from a halo perspective observed back then. Well, at least missing from the hot phase. But if you think about these groups, the intergroup medium, and I have spent a lot of time working on that from the simulation perspective, you cannot find those baryons in a cool phase, such as in the UV. There's just not enough, and that has been revealed through various surveys by COS, and we can't account for them in the galaxy component. That's only a small fraction of the baryons. But you'll also see that some of my favorite models here, like Model 2, Model 3 especially, are underpredicting some of these ERAS-4 stacks. And we're not trying to calibrate to that data either. And I say that that is okay. But why? Well, it's important to remember that we're only modeling the atmosphere, the 1D atmosphere, and there's surely clouds, and we want to release this for cool cloud embedders, such as Yaka Fairman, who wanted to be here, but is not. And if you are on a telecon with Yakov or see his office, he has a picture of clouds like this because he's thinking about clouds in an atmosphere. And he has his own models for the hot atmosphere and, some isothermal models and an isentropic model, or Cloudflex by Cameron Hummels, and others. So we want to combine this ultimately with a cool cloud model as well. But I'm going to focus 2 more slides on the X-ray because it's a little bit new. So here are the profiles for those ERAS-4 stacks from Yi Zhang. And it's a little bit of a busy plot, but the data points are in, our points. The observations are data points, I should say. And the models are lines, and they don't always fit. And especially for for the Model 3, the slope-changing model, they're underpredicting the observations. Now, if you go deep and observe deep with, XMM or Chandra, really it's XMM that has the capability, the soft X-ray capability, for hundreds of thousands of seconds, you can see structures associated with, normal galaxies, L-star galaxies, the CGM, that are not spherical. They're biconical outflows or structures probably associated with outflows. I'm thinking of Edmund Hodges-Kluck, and some other papers, recent papers, showing that there's another component besides the hot atmosphere. And we'll say that there are X-rays associated with non-1D structures, which may be better representative of the intercluster medium and the intergroup medium. But it seems like by the CGM, things have changed. So in this paper, I make these, I think I changed the y-axis, the title of the y-axis here, but this is taking my model and comparing it to the, ratioing it with the observation. So if the model's too bright, the model over observation ratio is more than 1. And you can see that model 1 will often just comprising, summing over all these data points, comparing the model to the observation. Sometimes that model 1 will be much too bright. And that's the problem we were having with in the previous slide, showing the X-ray luminosity of these, intermediate mass halos being too bright. Or model 2 sometimes underestimates. And model 3, I said, okay, the shape is more similar, and that's by coincidence. I didn't calibrate it to this, but there's still a spread in these model over observation ratios. There's 2 more violins over here. I'm not going to go into that. You can ask me about them. They have actually different dispersions for the density. So at that point, I want to take this time to kind of pivot to groups. And this is the XGAP project, which is 39 groups, about 10 to the 13 to 10 to the 14, observed out to approximately R500 in the X-ray with XMM. And this is data that's already been taken, but this is actually from the proposal here on the left. And XCOP is what we calibrated to for the clusters. So groups for normalized entropy show higher entropy profiles, more entropy relatively compared to the self-similar scalings. And that corresponds to fewer baryons and potentially higher temperatures, actually, both of them. And that combines to have puffed up entropy profiles. And that's something that we have in our model. And it's actually kind of like a rough physical criterion for model 3 to not have entropy slopes that decline as a function of radius, at least for most halo masses. And if you think about, if you know Jakob Fairman's isentropic model, it's kind of similar to this at 10 to the 12 at Milky Way halo masses. So the point is that these models form a continuum. It's not the right answer. There's likely more complicated things going on with feedback from stellar winds, from AGN-driven winds, etc. And if you look at simulations, they have different relationships given the different feedback prescriptions in those. But this is just a simple, relatively simple, more complex than we initially envisioned 1D model to model these atmospheres. So I'm at 227. So I'm going to touch on UV oxygen 6 column densities compared to the CGM squared and all the compilations from Chernyshiev. And it's a complicated plot. And I wanted to model oxygen 6 because, from simulations, I'm inspired by this model, and so is Nastasia Weiters, who's here. Is inspired by this virial temperature thermometer model, where the collisional ionization temperature of each ion peaks at the virial temperature of different halos. So 10 to the 5.5 Kelvin oxygen 6 peaks at lower mass halos. And this is why we argue, looking at Eagle and Eagle CGM simulations and others, Lester's TNG shows this, others show this, there's a peak around these halo masses often corresponding to the virial temperature in the outer halos of these, star-forming galaxies. And by the time you move to passive galaxies occupying more massive halos, your oxygen is ionized to oxygen 7 and oxygen 8, and we make predictions for those with the various models to inspire X-ray spectrometers. Hopefully, far in the future, near in the future, who knows when, something can detect these in the X-ray in terms of absorption. And Nastasia has other ions as well. It'd be great to get iron 17. That's a very different one. And you can use TPM Halo to make predictions. And pressures, the other UV observable, I'll touch upon. Mark Voigt has compiled these, working with Jess work, and others, and Xiaowen's group, and just a whole set of observations from COS Halo, COS LRG, COS GTO, showing the individual data points and our models, which have higher pressure. So even in reduced pressure models compared to that self-similar scalings, the pressures are lower, but they're not low enough corresponding to the pressures derived from cloudy modeling of these 10 to the 4 Kelvin clouds. So you want to invoke maybe a non-thermal pressure support mechanism in those cool clouds. Does that apply to the hot halo? We don't know. Right now, there is still a significant overprediction of the model pressures, especially in quiescent, more massive halos generally than star-forming halos. But there's still problems. And this is going back to Jess Work's famous 2014 paper. Okay, so this is the summary of DPM Halo, which you can make a lot of these plots already, and by using pip install DPM Halo, and we want to get the paper out. And I was talking to Johan Kompret, and he's very excited about this because the package is meant for both gastrophysics investigation. So maybe you want to have a realistic, atmospheric conditions for your wind tunnel simulation if you're doing a theoretical exploration like that, or you want to calculate how satellite stripping is occurring as dwarf galaxies are accreted into the Milky Way halo in the last several gigayears. I'm thinking about Mary Putnam here, and we're actually kind of working on the last pieces of applications for DPM Halo to inspire the community to use it. It's also meant for cosmological applications. If you need a baryonic profile for hot gas, in large surveys and around groups and clusters. Most of your gas, most of your baryons associated will be hot. And this is Johann Comperet's like cross correlation of all E Rosita, ERAS4, I think X-rays. I'm not involved in this paper, but we were inspired. Like he has a LX-M500 relationship, and he said like we can do better than that. Let's use DPM Halo for this. And he's cross correlating every X-ray detected by every astrophysical X-ray detected by E Rosita. And it's a really interesting paper. It's mostly AGN, but there's a CGM component or hot halo component, CGM, ICM, IGRM component as well. So that brings me to the end of the first part of the talk, the biggest part of the talk, and I'm going to move to a higher dimension now. And I'm just going to make sure everyone's there. Jess, am I being heard all right?
You're doing great.
Okay, I'm going to take a drink of water and talk about something else from cycle 31. That's finished in one way, but not published. This is a program observational that Glenn Kapsak Les is leading. We call it COS Edges. And it is using an observational strategy to pick sight lines along inclined disk galaxies that are probing the semi-major axis, the accretion disk. So here's, a quasar galaxy pair. I think can figure out which one is the quasar and which one is the galaxy. Reviewers of this didn't always get that. It took a few times to get it through. And we're really probing the inner CGM here. And here, the inner CGM is inside 35 kiloparsecs. And this is, the bottom right is a little bit technical. That is something from what we call the major axis CGM survey. And these have been already detected in magnesium 2, but we want to get more ions, including oxygen 6 and the Lyman series. So the average redshift is 0.2. The goals are to understand the kinematics in multiple ions, derive metallicities, really delve into the multi-component physical structure. And here's kind of a busy slide showing some results. And we have rotation curves for these, thanks to Glenn's observations. And you can see this has been known for a while, and Glenn, I think, really pioneered this, is you see absorption that is co-rotating at CGM scales with the rotation curve of the galaxy. We see that again here. And in fact, we can contrast the rotation curves in different ions. And I'll give you a more of a summary plot in the next slide. But I think all 9 galaxies, it's a 9-galaxy survey, show co-rotation and in most ions. We can combine all of these together. Glenn did all this work. I did almost nothing here yet. But it shows in the inner CGM, there's co-rotation in all species, from oxygen 6 all the way to magnesium 1. I also want to say that oxygen 1 is detected more than half the time, and that's exciting because you can take oxygen 1 and compare it to H1, which we have in many different Lyman lines. We don't get Lyman alpha. We're using the G130M grading, but these are already detected in magnesium 2, so we're sure to get strong H1. So we have a lot of H1 data, and there's a trend that there's every ion, high ion and low ion, is showing co-rotation. There is slightly more co-rotation with the low ions than the high ions. I actually predicted that oxygen 6 would show less co-rotation, much less than shown here. So it's a little bit of a surprise to me that oxygen 6 shows as much co-rotation. I expected some, but not all of it. So if you think about the first part of this talk, that 1D atmosphere static halo, well, this contradicts that. It suggests that most oxygen 6 detected here is co-rotating from a different component. the bottom left here shows the outer CGM here beyond 35 kiloparsecs out to about 100 kiloparsecs, showing less co-rotation, especially in oxygen 6 compared to the inner CGM, which is consistent with velocities almost at the velocity of the rotation curve of the galaxy. So that's quite exciting. I think this data set turned out as good as we could have possibly expected from this survey. So that brings me to my final part of the talk, which is really a future direction. And this is the 3D TBD CGM, the structure of outflows, and in a new waveband that I haven't even talked about yet, that I didn't really know much about until October last year, is molecular outflows. So to ground ourselves in the UV and looking at magnesium 2, you expect an enhancement along the major axis, and that was the cost edges survey. And you might expect an enhancement in the minor axis due to observations here compiled by Crystal Martin, and also Robin Bordeloy and Stephanie Ho and Glenn Kapsak, and all that really nice work and a compilation of it. So magnesium 2, I would expect to be enhanced along the semi-minor axis and possibly associated with high velocity outflows. Nicolas Boucher is here, and I need to shout out to him as well because he has observed outflows at several hundred kilometers per second in Meg-2 around a number of galaxies for a while. But molecules have been observed around nearby star-forming galaxies, and this is thanks to molecular hydrogen vibrational and rho vibrational transitions in the near and mid IR. And our favorite outflow galaxy M82 shows H2 extending several kiloparsecs above and below the M82 disk in molecular hydrogen. As well. This is ground-based. I forget from what telescope, but from a well-known observer of this. So what I learned last fall was that JWST is detecting these H2 rho vibrational lines around nearby galaxies. NGC 3256 is a paper that kind of inspired this investigation, or this proposal, I should say, of molecular lines observed in, there's at least 8 mid-IR lines, and they're much thinner and higher resolution, I should say, for this object, which is 10 times further away than M82 and is a merger. But M82 is definitely a target. But if this Spitzer spectra here shows much broader lines, reduced sensitivity. So this data set down here from JWST MIRI is just so rich in data. Dust astronomers are very excited about it, looking at PAHs, etc. We thought we would put together a proposal to look at the molecular hydrogen in these idealized simulations. Hence my visit recently out to visit Alex Richings at the University of Hull and his 2 graduate students, Elliot Howitson, who's really working in the outflows, and Oliver Thompson, who actually has a paper out, looking at fire to CHIME simulations. And CHIMES is Alex's module. It's actually, I've worked a little bit on it, but he looks at molecular species in non-equilibrium. I look at the ions, but I haven't worked with these simulations yet, but they're out. I have nothing to do with these simulations, but we did get this grant to actually put these simulations and some future simulations through mock JWST observations in anticipation of a number of observational campaigns. The most relevant is one by Sylvain Veilleux, who's was our observer guide on this proposal, and really helped us get it over the line, I'm sure, with his expertise. But he has a really nice cycle 3 campaign looking at not just M82 and some, poster children of edge-on galaxies, NGC 891, NGC 253, but a number of others. It's a pretty big investigation. So they're looking at dust, but they're also looking at molecular lines. And we predicted, or I should say, Alex and Elliot and Oliver predict that the non-equilibrium is a significant effect, especially for the extended H2, above and below the disk, a few kiloparsecs. So these are idealized simulations, but they're beautiful, and it made a nice, easy to make a nice plot, and I should say warm, hot, and cold reverse to a very different temperature scale that we're not used to in the CGM. So that is a future direction, which I think will tell us a lot about outflows via JWST. So I think I finished in time. I probably could answer a few more questions. I went a little bit fast over those last 2D and 3D parts of the talk, but I want to have a few takeaways here. The 1D DPM Halo is available now, and it's just been, we have a mathematical problem describing something is delaying the paper. And Mark and I want to be very precise about it. We want to check our math. It's just a little thing, but it's ready to go. And you can do pip install DPM Halo and make a lot of the plots here. 2D cost edges is for the AxiSymmetric CGM accretion disks. So my personal takeaway from that is in the remaining time we have COS and Hubble, and we want to get, I would say we want to get rich multi-ion data sets for the greatest legacy value. And then 3D is JWST opening a new window into the complex, maybe Flockian, maybe like chimney-like structure, I don't know, of molecular outflows extending into the CGM. And it's not just superior spatial resolution, but it's spectral resolution. And there are IFUs, IFS on JWST that can, really, revolutionize this window. So that's my summary, and thank you, Jess. Thank you, Xiaowen, for having me give this talk, and I'm happy to give answer any questions. All right, and I'll sit down now.
Thank you. Wow. What a whirlwind tour through the CGM. All right, so I think we're gonna open the floor to questions. So everybody here, the raise hand button, if you're not familiar with it, is at the bottom of your screens there. Go ahead and I'll just call on people in the order that I see hands. All right, Varsha, first up.
Yes, hi Ben. Thank you so much. Wonderful talk. I had a quick question about your second part, about the 2D.
Yeah.
The co-rotation. Can you please describe how you're defining the co-rotation? Is it in terms of equivalent widths, or is it in terms of column densities?
Oh, for this first paper, it's just in terms of equivalent widths. There's not column densities yet in this first, like, in preparation paper. So
okay, because that could make a difference, right?
Yeah. It will make a difference, I imagine.
Right.
Yeah. Can see that there's definitely saturation, right?
Yep.
Carbon-3, I mean, this is a new play I haven't really thought about. Like, carbon-3 is sometimes stronger than H1, right? Actually,
right.
I actually have to, that's probably Lyman gamma H1. So yeah.
Okay, all right, thank you.
Sure.
Looks like Anna's up next.
Yeah, hi Ben, thank you for your talk. Since you were on this slide, I was just gonna say that, and I'm not, I'm not a UV expert, so I'm not 100% sure what you're measuring here, but in X-rays for the Milky Way, sorry, someone unmuted. Okay, yeah. So for X-rays and absorption for the Milky Way, we have hints of this similar co-rotation with like similar velocities. So one paper is actually by Edmund Hodges-Clark from, I think 2016. He has some good velocity constraints. I wonder if, if you add that information, if you can gain some more insight. So just a shout out that, yeah, only for Milky Way, because we don't know where this gas that's absorbing in the Milky Way that we call CGM is. We have no distance information. So if you could tell us that it's maybe on similar scales, judging by velocities, that would be interesting. Thank you.
Yeah. Yeah. So yeah, this is where like I have many different hats that I wear, and one is that the Milky Way is or the CGM and is not 1D, and if you look at clusters and groups, I'm going to get to this in a little bit in a roundabout way, and clusters and groups are clusters especially are like pretty consistent with hydrostatic equilibrium. And I looked in, a lot of the eco-CGM zooms that I ran and worked on and was an inspiration for the variable temperature theorem model. And one thing that came out from the eagle zooms was that the inner CGM was co-rotating, and it was the hot halo that was co-rotating at about half the virial radius. The cool CGM was co-rotating at, the virial velocity. And the cool CGM was co-rotating at the full virial velocity. The hot CGM was co-rotating at about half the virial velocity, thereabouts, and that provided a lot of support. And you broke that hydrostatic equilibrium model, especially in the inner CGM of normal L-star galaxies. And a huge amount of that motivation was Edmund Hodges-Clark and other papers in Joel Bregman's group showing that O7 absorption from the Milky Way it's very difficult data to work with, and it wasn't uniform all over the sky, but it was consistent with co-rotation of a hot halo going at 180 kilometers per second, which is close to the virial velocity, a little bit below the rotation velocity. I think we're at 220 kilometers at the sun, kilometers per second. And is that gas like in the the thick disk in the disk halo interface, or is it hot halo gas? And that's a great question. But what Anna, what you made me think about here is that thinking about O7 in the X-rays and this data, and we really haven't thought about that. So that's a great point. We don't know the answer, but we should consider that. Okay.
All right, we got another question. David.
Yes, thank you. Wonderful talk, Ben. I was wondering, is there a way to include explicitly the clumping factor of the gas in DPM halo?
No, that's up to you. Okay, so yeah. Oh wait. Roughly, okay. I like to just put other work on other people, and I'm like hoping to do that. But wait a second, I was like, I shouldn't answer that so fast. There's a feature to this model that there's clumping. There is a parameter for clumping, and I really never thought of it that way. But there's this parameter sigma NE, and that's like the 31st parameter. And we have pressure at a given radius, everything has the same pressure in DPM halo as it's in its current incarnation. But I allow a spread in densities and a corresponding inverse spread in temperatures. So you could say that that is like a clumping factor in the in the density structure of DPM halo. And that doesn't matter. The way the formalism has been written, calculated, is that doesn't matter for things like Sunyaev-Zeldovich or electron column densities through the halo that's preserved. But for UV absorption, it matters a lot, and for X-ray emission, it matters somewhat. So there is a clumping factor. There's a log normal spread, I should say, in densities and inversely in temperatures, which I felt it was inspired by a little bit by simulations and the reality that you have a dispersion of densities necessary to model, especially oxygen 6. Yeah, so yes and no. I think there's not a full clumping factor. If you wanted like a clumping factor for the cool phase, you should put that in your cool cloud model. But there's a capability to have some sort of clumping in the hot phase.
So are you expecting the clump factor to be higher at larger distances?
And at larger distances. Uh,
Well, not. Let me think about it. But
okay. Yeah. Well, you made me think of a 30-second parameter. How does sigma NE change as a function of radius? This is something that I hope people are able to add if they wish, and if they have like some reason to expect that. It's the same at every radius as currently parameterized. Would you expect it to be higher at other radii, outer radii? I don't know. That'd be interesting. But yeah, no.
Okay.
Yeah, and if you have a reason for like asking that, feel free to share it. I have or talk to me offline. I'm interested in your line of thinking.
Yeah, will do. Thank you.
Any other burning questions? Oh, we got another one. Nicholas.
Yeah, hi Ben. Great talk. Just a comment and a question. The comment is, I think the kinematics and the co-rotation is great, but I think has been seen already before, like 10, 15 years in small samples. I think the new thing now is the different ions that
Yeah.
we can trace in the same data. But leaving the kinematics aside, what do you think about the prospect of tying up the three parts of your talk in terms of different phases? You talk about hot gas, and then magnesium 2 traces mostly the neutral gas, and then you talk about molecular outflows. What are the prospect of combining in the model or in observations constraints on the hot, neutral, and molecular gas?
Like a holistic model that simulates everything.
Or if you think that you can make predictions, or one could make predictions for these different phases, especially on Milky Way like halos. I think in clusters is dominated by a hot gas.
Yeah, yeah, yeah. This is a modeling effort here. The first part of the GPM halo is yeah, it's a basis in a very simplistic start to that process, and uh, there's I think of there's definitely many analytical models out there, many analytical treatments, and I have a slide on it I didn't show, talking about the different analytical treatments, and there's still like there's different some are like there's precipitation, there's isentropic models, there's interior virial shocks, there's rotational cooling flows of Jonathan Stearns. I actually skipped that slide, but already like a lot of those are inspired by simulations, where you do have everything but not at high enough resolution or not in enough objects or in an idealized simulation. Would you want to use DPM Halo as a basis for something that has AxiSymmetric inflows and molecular outflows as well? That's a tall order. There's the formalism for that. There's other formalisms out there as well. And I think there's AxiSymmetric models where you could input cool clouds as well. I think of these. We should reference this in the paper. These Sormani models with the AxiSymmetric simulations or analytical models that are AxiSymmetric in with rotation in them. And using that as a template, I would almost start with that for something, that complex. Yeah, getting this like to something where you're modeling like something as complex as the Milky Way. That's several steps away with this model. And that makes me think like maybe like how should we push this model to go in that direction? Because we don't assume hydrostatic equilibrium here. I make those plots. Actually, I don't put them in the paper. You're capable of making those with the DPM Halo package, but that's just 1D. So yeah, it's
Thank you.
something to think about. Yeah.
Okay, well, we're getting to the end of the hour here, so I'm going to suggest that anybody with remaining questions get in touch with Dr. Oppenheimer, and I think we owe him one more round of applause for a really fantastic talk.
Okay. Thanks, Jess. Thanks, Shawan and Erica too, I see. Yeah.
Yeah, thanks so much for that. That was really great.
Okay. Yep.
I'm going to stop recording.
All right.